So hopefully I am recording. What now? First of all, I wanted to show you the syllabus. I did update some notes. I think I updated C2S7 as well as C2S11, and I've added C3S1. It turns out, though, that we have actually quite a bit to do in that C2 sections. It's actually sections 11 and few beyond that. As a matter of fact, these sections are some of the more difficult sections of this course. I did want to mention that we will not be covering at this point section 11 on exceptions. We'll come back to that a little bit later. I will reference a few of the simpler cases as we go through the code. And the assignment, did I say it was due Wednesday a week? Is that Wednesday a week? What now?
9 days from now. So
What now?
yeah, it's 9 days from now, so a week would be Monday, 2 days
Yeah.
would be
Yeah, it's Wednesday a week it will be due. Again, part of the reason that we're spending more time on this first assignment is for you to get accustomed to R and how to submit it. Again, you should use a template, and I will send you a naming convention for this, because I don't want everyone to send me a sign ASSIGN1.RMB, and I have no way to tell which file is with which person, in fact, with which class. So I'll send you a naming convention that you can use to rename the file. And it's the .ormd file that I will warrant. You can send me the HTML file if you want to also. In fact, if you're unsure whether you think I'm not going to get the work, you probably should send the HTML file, as well as the .ormd file. So this is pretty much up to date. So I will bring up, if I can find it, oh, I have to refresh it. I hope that this is the latest version. I hope I didn't. Yeah, I think it is. So I'm going to do a couple maintenance things here. I'm going to clear the console. I'm going to set the working directory to chapter 2, and take a look. I'll leave the workspace open. So as I mentioned, I'm going to save the exception handling for a little bit later in the course. Basically, the exception handling deals with the fact that you have code and you want to catch certain types of errors. And there are certain constructs that are built into R, like called try, catch, certain functions that allow you to catch errors and then do something with them. Again, this is something that you'll see in most modern languages now. Now, I had gone through section 12, but I just want to spend a few minutes. I've added some textual material, and I went through some detail that R is a pass-by value, which means that if you call a function and you need a parameter in that function, an argument, that R is actually going to pass that value to you. And it may or may not make another copy of it, though. It depends on whether or not you actually modify it. So if you have a large data set and you just need to extract something from it but not modify it, it probably will not copy it. It will probably just leave it where it is and copy what you need, as long as you don't change that particular data frame, let's say. I then discussed you know, the evaluation, the standard evaluation model, if you have like 1 plus 10, that that's parsed into a call to the function plus, and plus is actually a function. And then the 1 and 10 are actually arguments to that function. And you start getting into, and again, I've sort of enhanced the notes when you had them last and changed some notations. I think I'll go ahead and hopefully this will run. I'm going to go ahead and bring up the HTML file so we can look at it a little bit. Okay. Because what I'm doing right now is primarily review. We've done this before. So, one of the issues for any symbol you put into R is that symbol will have some binding. In other words, a symbol may be bound to a function. It may be bound to a value. It may be bound to a very complex data structure. But how does it find what it's bound to? Well, the standard evaluation model uses a search path. If you use the function search, which we've done, with just parentheses, it will give the search path that it will try to find the binding for any particular symbol that you would type in to the console, to the R evaluator. And so, and it finds the first instance. Now, it also, if the type information is variable, it finds the first instance of the type you want. So if you find something called F could be bound to a value, it could be bound to a function. Well, if the R evaluator knows that it's looking for a function, it will find the first instance of the symbol that's a function. And so, so there is a little bit of intelligence when R tries to find what you're looking for. Now, the problem is that you can have more than one, you can have the same symbol bound to different things in different places in your search path. So the reason is you can dynamically create functions, which creates a symbol of a function in your global space, let's say. You can also attach packages, and a package may actually have the same function name as the one you just created that you wrote. You don't know. Someone writes a package, and there are thousands of people out there writing these packages. You don't know what they called all their functions. So you could accidentally, and you may need their function, but you write one that just happens to have the same name. So when you try to type in the symbol, you don't find the function you really wanted. You found some other function. So we have to have some smart way of dealing with this particular issue. Well, one of the things that will help you is define. Find will tell you all instances of that particular symbol. And it will order them in the order it will find them. And then get actually gets the binding to that symbol. So the find and get are pretty powerful tools that you'll need. So let's see if we can go down here. So if we take the plus, and if I simply say find, it's in the base package. And if I say get, that's the binding. So plus is bound to a function in this case. And this function has two arguments, E1 and E2. So in the case we had 1 plus 10, E1 will be bound internally to this function. It will be bound to 1, and E2 will be bound to 10. And then it calls this dot primitive plus, which is actually C code, which actually does the computation. So the actual code that does this is not done in R, it's done in C. It's a primitive function that's built in. Now, suppose I redefine plus as a function, but instead of printing the sum of the two arguments, it prints hello. So what happens if I do find now? So if I do find now, it says I found plus in two places, the global space. Notice down here, That was me. That's when I just created it. It's a function in my global environment. And so there are now two instances of plus, one in the global environment and one in package. So what happens? What happens now? Oh, and if I get plus, that's the value it gets, right? It gets the first one. So what happens if I say 1 plus 10? The result is healthy. I mean, this is a silly example, but take it seriously. Because this can happen to you, and you're trying to figure out, why isn't this working? I am masking the real plus symbol I want by this silly plus function that we define. Okay? So what happens if I remove plus? The remove moves it from the, REM removes it by default from the global space. So if you watch the lower left, it removed it. Now what happens when I say fine? We're back to what we want. And of course now, if I say get, I get what I want, and it evaluates the way I want it. Okay. So we also have non-standard evaluations. In some cases, a function does not really evaluate its argument, but instead actually returns something like the name. If you consider the function library, by the way, library probably should be called, that's a bad name, because it really probably should be called package as its function name. Because what it does, if I have a package called tools, what it does is it loads it into the search space. So if I type in search, then there should be tools in here. Actually, the tools was already in, but previously. But when I say library of tools, it doesn't actually evaluate tools. If I were to put quotes around it, it would evaluate it as a literal. If it would evaluate tools, what would have happened? Well, what is tools? Is it bound to anything? Is it a symbol? No, it's the name of a package. It's not a symbol. It's not bound to a function. It's not bound to a value. It's the name of the package. So clearly, that function library did not really evaluate it, because if it would have returned an error. So library, I can put the name of a package in there. It doesn't really get evaluated. And so this happens on occasions. So it's not a symbol, and it's not a character literal. So following our standard rules, that would not work. Okay, but library as a particular function has some code in it that bypasses the standard evaluation. It actually uses a function called substitute, and what it does is it actually returns the symbol. And then ultimately, if you look at the code for library, and you can look at the code for library if you like, if you look at the code for library, what it actually ends up doing is mounting that package in the search path. Now, there's a little bit of complexity that when we talk about function evaluation. So I like to talk about function evaluation, and this is a fairly subtle topic. And we'll sort of see why in a moment. You have a global environment. So if I say x gets 2, and x is a symbol that's bounded to in the global environment. So if I did that, if I say, x gets 2, then here it is in the global environment. If I define a function, like I did previously, it's a symbol in the global environment bound to a function. But what happens when you evaluate the function? And this can become fairly complex. So when a function is evaluated, it creates what's called a new environment or a frame for the evaluation. And this frame provides bindings between the formal arguments of the function. In other words, when I pass values to those formal arguments in the function, and I'll do examples in a little bit, then they're bound within this environment created by the function. So this seems all, it seems pretty straightforward. I have a simple function, and like f of x equals x. And so I pass it a value 2. So what does it return? 2. F of x, if the value is x, so it just returns x. So I pass it 2, it returns 2. Or you could say x plus 2. And so if I pass it the value x equals 2, if I pass that value to the function, it returns 4. That's simple enough. However, suppose I say f of x has the value x plus a. So now you pass it 2. A is called a free variable because it's not defined in the function. It's not bound by an argument. So how does it get the value for A? Where does it look for this value? Now that becomes a slightly more complex problem, and we'll come back to that in a moment. So, because you can have functions defined locally, you can have variable bindings locally within a function, but you can also have them outside of the function in what's called the global environment. But in reality, you can create an environment, the global environment, and then within it, you can have another environment, and then within it, you can have another environment. You can think of having environments within environments within environments, and then the question is, you could have variables defined in each of these environments. So where do you get the value? If you have an inner environment, and it has an A, and it's not defined in this environment, where does it find the value? I'll come back to that. The point is, if you have a function that I define, it has a parent frame. So if I define a function f in the global environment, then the parent is the global environment. That's called the parent frame. So symbols that are in the global environment have no effect when you have a function in R, at least, when you have no effect within a particular function. So we'll have to define in a moment how this works. If you have a language, however, where the symbols in the outer environments affect the inner environments, then that's called a dynamic language. Now, there are advantages and disadvantages. Languages that are not dynamic, strangely enough, are called static. They're also called lexical scoping. But you might think that, you might ask, well, when is a dynamic language good, and when is a static or lexical language good? And it turns out there are strong reasons for using each. And in some ways, it might be better to have a hybrid in which you can have a dynamic language as well as, in certain cases, lexical. But why would you maybe want a dynamic language? And when did they become somewhat popular? Well, they became popular with graphical user interfaces. Because you click on a mouse, you want an immediate response. I change an external thing by clicking on a mouse, you immediately want a response. So if you have a dynamic language, it can be much faster when with graphical interfaces. So if you look at the programming model, if you look at the programming model on OS X, which is underlying the Mac system, it's Objective-C, which is C with extensions to C, in order to do what's called object-oriented programming. But it also is, at least you can define it in a dynamic way. And the advantage of doing that, again, is for graphical interfaces. It can be extremely fast. Now, it used to be there was some penalty for that, but it turns out now there's almost no penalty for having a dynamic language. Well, if I've got these environments, we also call them frames. We have frames within frames within frames, or environments. It's the same thing, a frame or an environment, just two different terms for the same thing. It turns out that you might want to be able to sort of track yourself up this series of frames. Now, often you don't have that many, but there are a couple functions. So, for example, you can say sys.frame which equals 0, and that tells you that the frame 0 is, in fact, a global environment. And sys.parent n equals 1, that's sort of the first parent, not your grandparents. What that actually does is that actually returns a counter 0 in this case. If I do sys.frame of parent.frame, it actually gives the parent for any particular function, let's say. Well, this is something that, if you read the book, they say, well, we don't really encourage you to do this unless you really seriously know what you're doing. But you can do it. So in other words, if you look at the documentation for these sys.functions, they allow you to go up the stack, and they let you find the variable. If you think of each environment having certain variable bindings as you go out, and you want to know in a particular level environment, let's say I'm 2 up or 2 in, or however you want to view it, I want to know what bindings are in that environment. Using these sys. Functions, you can actually find the bindings in a particular environment. Now, that gets, usually your environments are not quite this complex, but I am going to show you some examples later on where this occurs. So I'm going to define a function foo. So what does foo do? Foo is a function of x. Okay, it's a function of one thing, x. So x is the formal argument. And this says, and this can kind of review some of the if statements and so forth. This says if x is less than 3, remember the if-else we talked about, but I don't think I gave you an example? I had an if-else, but this is just an if, and then it has a separate else clause. So there was an if-else as one symbol, and then there was an if, which can have an else separately, and I don't think I gave an example, so here's one. If x is less than 3, that's either true or false, right? If it's less than 3, then it tries to add the null list to x. Else, if x is less than 10, warning, ouch. Now the warning just prints, it's going to print that out. Else, if it doesn't meet either of those conditions, it's going to print 33. Okay? So now I'm going to say b get foo. What does get do? It gets the function. In this case, it defines it to b. So what is b? What is b? If I would print out b, what would I get just by itself? I get the same function. So I've assigned the function foo to b. So b is a symbol in my global space. Now foo is also a symbol in my global space, but I've defined a symbol b in my global space, which actually is foo. So what do you think is going to happen if I say b of 23? What's going to happen in that particular case? It's 33. No problem, right? It's not less than 3. It's not less than 10. It's 33. So it returns the value 33. Okay. Now, on the other hand, just to show you what would happen if I'd say b is 7. Ouch. Winning message. Now this is part of that. That's part of that section 7 I skipped, where it talks about warnings. But you can see that some of the things are quite simple to do. And what happens if I do b of 2? What would happen if I do this? Error. You see, the problem is I can't add list to x. X is well defined, but I can't add list to it. Okay, so it's not going to work to try to add that to a numeric number. It can't convert it. It can't coerce it. It doesn't know how to convert it. If you would add a character string that has 2, it may know how to convert that, but it doesn't know how to convert this. So it can't coerce it, so it gives you an error. Okay. Now, there are also some other functions. DoCall is one of these. And I can say, for example, DoCall foo, and when I do this, the DoCall says the function is first, and then I call it with some argument, but it has to be specified as a list. And so if I do that, DoCall with list x equals 23, then that actually gives me the exact same thing. Now, you would say, well, why would you ever want to do that? Well, you probably don't want to do that very often. But it is another way that you can call a function. And it does have a few features that you don't get in terms of how you control the call, that you don't have just a standard way of calling a function. Now, this next one, however, is important. With list x equals 23 foo of x. If I do that, I still get the same thing. And you might say, well, this seems like a lot of work. Why don't I just say, why don't I just say b of 23 or whatever? Why don't I just do it that way? A lot of times you may have a bunch of data frames, and that first argument can be a data. It actually can be a list. It can be a data frame, or it can be an environment. The most common way this is used is that we want to call a function on the variables that are defined within a data frame. So where we usually use the with is when the first argument is a data frame, and then we want to apply a function to the specific value, the specific variables in that data frame. Yes.
Is there any advantage using that over like apply function?
Well, apply, again, I may have multiple data frames, and they in fact may have similar names or whatever. So I may want to apply, it's sort of a different thing. I want to apply this. It's not, apply is a function we will be looking at, but apply is a very general type of function. And here, this may be that I want to do this analysis on a specific data frame. It would be like if I had 2 jump tables open at once. And I click on this, and this is the active one. And now I can do operations on it, whereas I click on another one. So this means I'm restricting my functions to a particular data frame in this particular case. That's where it's most often used. But it is more general than that. The apply function is actually sort of a different type of beast. It's a specific function that I can apply to, say, a grouping. There are a lot of applied variations that we'll talk about a little bit later.
Can you talk about the difference between with and within?
I haven't used within. No, we can look.
It tells you in the.
Does it mention it in the book?
Well, if you search with, it actually has within there as well.
Oh, that's often the case. I don't know. Let me take a look at that. Exact same arguments.
I think it's the order that's the difference.
Oh, yes. And this actually, it is the order. This is with is a generic function that evaluates expression in a local environment constructed from the data. And you're going to see something that I think I do have an example similar to this coming up with the eval function, where you really get fooled. It's a similar, except it examines the environment after the evaluation of expression. And so there's another thing I'm going to show you a little bit later on, which is almost identical to this and how it does it. Because if it does it after evaluation of the expression, that can lead to unexpected consequences. And I'll show you an example with the eval function in just a little bit of something very unexpected. So I was just reading it a little bit more, but I'll take a look at that. I don't know if they give some examples comparing them down here. By the way, unfortunately, I don't see any within examples. I love it when they do that.
No, right?
By now. Okay. Are there any questions on this? Evaluation on an exit. A lot of times you may have opened let's say, a connection. You may have a remote connection. You've opened some remote connection to another server or something. And so a lot of times when you quit the function, you want to make sure you close down that connection. And so the onExit it's a function, and the function allows you to do sort of cleanup operations. So you're going to exit, but before you exit, you want to clean up things like close down the connection if you've left the connection open. Maybe it's what's called a socket connection to some other environment. And so you want to close that down before you actually exit. And so I don't have an example of that, but we may have one later on. This is the type of thing when we were in the 623 course where we get into a lot of web technologies. That type of thing becomes very important, that you close these external connections, for example. Now, a lot of times the other server will, if you didn't do it properly, they often, at some point, they're going to automatically cut you off. They don't leave it open forever. But it's polite to close them. So, now, and this is a little bit subtle. Other topics is really referring to what are called side effects. See, all functions return a value. It may be null, but every function returns a value. But in some cases, functions have what are called side effects. So what happens when I say print A? The actual, what you see printed is actually a side effect. So if I say print A, that A I'm trying to get this down a little bit. That A is actually a side effect of the print function. But print actually does return a value. So if I say V gets print A, it actually gets a value. And the value happens to be A. But there's really a distinction here. Because if it returns a value, I can capture that value. You can't capture the side effect. In this case, the side effect just prints. But I actually can capture the actual output of print, and I could use it in some other. It's a symbol. You notice V is defined over here in the. You see V? It's a symbol in my global space, and it has a value A. And so I've created a symbol, but that actually was not there until when I just said print A. Well, maybe we can sort of take a look at this. So if I say, let me do this again. If I say remove V, V is gone. So when I say print A, do you see any V? In other words, nothing appears. You haven't created anything. Nothing appears. But when I say V equals print A, now watch what happens. Notice that V appeared here. So that's a symbol within my global environment that appeared. And, of course, I can evaluate v, which actually I already have. But well, actually, I haven't. Because what happened is, when I said v equals print a, this a that got printed was the side effect. That's the side effect. The actual value is here. So this may seem subtle, but some functions that either you write or are built into R, they will return a value, but what you see printed out by default may be a side effect. In other words, it does something as a side effect, which is what maybe you see. So there's a distinction between side effects and the value returned by a function. Okay, now we're going to get into the eval, which is what I was referring to earlier. Eval evaluates an expression, its first argument, in an environment. But complex expressions are often wrapped by what's called a val Q, or by a quote, which corresponds to a function called a val Q. In other words, a val Q, in essence, quotes its argument. Now, this is again a little bit subtle. So I have two functions. One is a val and one is a val Q. That's much like the with and the within. And in fact, the actual way these work similar to that as I read it. So if I say x equals expression, and then I print out x, x is bound to that expression. So x over here in your global environment right here is bound to the expression. Okay. Now what if I say eval x? If I evaluate x, it actually does what you think it's going to do. Now what if I say quote x? Quote x just returns the symbol x. So then you might ask, what happens if I say eval of quote x? It actually returns the expression. See, did I? Yeah, I continue on with these arguments. So you might, sometimes you actually need the symbol name, and you don't want to evaluate. Okay, so sometimes you want the symbol name, and quote x will do that. That was sort of what happened when we had the library function, and we had library of tools. It actually, yeah.
I think this is left over from list.
What now?
I think this kind of thing is left over from
Oh,
list.
very much so. This is all coming from list. A lot of R actually. R is a very list-like language. The whole concept of lists, the lexical scoping, all of these things are derived from lists. Not the syntax. Originally, R was written in scheme, which is list. It's a dialect of list, and so R very much carried through the semantics of list, but not the syntax of list. So, you know, eval evaluates its argument just as you would expect. So I define x, and I eval x, and it evaluates it. That's what we expect it to do. So, okay, but eval q, it first calls quote. So these two were identical. So eval q saves you from doing line 234 saves you from doing line 235, if that's what you want. Okay. So at any rate, so the quote returns the value x, that is the symbol x, which is really the expression, is what it's bound to. Now suppose you want, and this is where things started getting subtle, Suppose you want the evaluation to take place in a specified environment. Okay, this environment is where eval or eval Q look for bindings. Well, let's take a look at this. Now, let's create a new environment. So let's call E as a new environment, and I'm going to bind X within the environment E. Now, did X appear? X is still what it used to be, right? Look at the lower left. X in the global environment is bound to this. X equal 10, X with the binding 10 is bound within the environment E. Now suppose I say eval X. Did I? What now? Oh, we have a problem now. This is Steve thinks we're losing that. What we do is we mount our file system. My directory gets mounted when I go into our studio. It gets mounted there, so I have access to the same file system no matter which server I'm on. And he thinks that somehow we're losing the connections between mounting it from one server to another server. What this basically means is that I need to switch gears. We still haven't. Yeah, this is not good. Steve's working on this problem. So what this means is that if I go back to the file system, you can do this, by the way, if you know how to do it. I went and I mounted my file system on this machine, and you can mount your file system from the server onto these Macs. The way you do it is you do something like that. You type, I said go to server, connect to server, and it brought up this. And if you do afp://stat.ww.edu:, well, the colon 12,000 I don't think you need here, but you need it if you're at home. So I just always do it. And if I say connect, then you can see my name is grayed out because I'm already connected. So, in particular, this directory path right here, J. Harner, which is me on the server, courses stat 523 notes chapter 2, is exactly the same. It's exactly the same as this path. Okay, it's the same thing. So now I've mounted this locally, and then I'm going to run RStudio locally. So now I'm running RStudio locally. Notice it's a little bit different. It says RStudio up here, whereas over here it says Safari. I'm actually running RStudio as a web app within Safari. And this is the one that's not working now. Okay. So I'm going to go back and run it here. And so what I need to do now is let's see. I think what I need to do is double click on it to get it to launch the right place. So if I take this file, that should automatically have loaded it. Let's see if it has. Yeah, it has. And if I say set as working directory, I may have trouble getting that to work correctly. You still having a problem here? I have to get back to have to get back to the basic mount point. It's going to create a problem. I'm not sure how to get back to the mount point. Did I do this last time? I'm trying to remember how. What I'm trying to do, I'm trying to get. I'm not going to get the correct. Maybe it'll work. But I don't have the workspace in the right place I want it to be. Now let's see what happens. I think I have to re-execute this part. Let's see what's going to happen if we do it. It may work out okay. I'm just going to go through and recalculate these. Okay. And then I'm going to create this environment. Oh, okay. Okay. So I create an environment E, and I bound a variable X within that environment. And then when I said eval X, when I did that, which I already did right here, it actually gives the X in the global environment. So when I say eval X, X gets evaluated in the global environment. Okay, so I have not, you know, if I look at X and it's looking for its value, eval is not associated with this environment, E. I created an environment E, but X is not defined within E. Nor is eval Q. So I have eval Q, which also returns the expression. Now that's what we would have gotten before. So when I evaluated eval Q, I'm getting the expression. When evaluate, nothing has changed. But what do you think is going to happen now if I say eval X, and then I say the environment is E? You would think that it would actually give you 10, right? So if I do that, I don't get 10, I get what's in the global environment. But if I do eval Q, I get 10. Now this is precisely that difference of the with and within. What happens with the eval is that it evaluates the expression first. And when it does that, it doesn't know about the environment. And so it gets the global environment. Whereas eval Q actually it sort of skips that first evaluation stage. And so it actually has time to learn about the environment, that it's actually in that environment, and so it actually gets 10. So this is an example, and that's sort of like what happens with that with and within as I read it. That the eval X, you would think, since I said environment equals E, you would think that it would evaluate X within the environment E, which means that it's bound to 10, and you'd get 10, but you don't. That's because it evaluates X first, before it knows about the environment, whereas eval Q does not. And I think that's really the difference between the with and within, the way I read it. It's a similar type thing. So in other words, you would get a big surprise. And this is the kind of thing that could drive you crazy when you're debugging a program. So this is another little subtle thing about how things get evaluated. Okay. Now, this is a function local, which evaluates an expression in the special environments in which all values, all bindings, and all changes are kept within that environment. Now, again, that's like, if those of you know Lisp, that is very much like let and various types of Lisp functions that will do a similar thing. I don't have an example for that function. I want you to look at this function. Now, this function turns out to be pretty hard. Can you tell me why? I'm going to go ahead and evaluate that function. And that function makes it available to us. And then if I print out GG, there's the function. So let's learn what this function does. GG, sorry, it does use local. It uses local, I'm sorry, GG is not a function. It's a local environment that has two functions defined within it. So GG is creating a local environment that has a function k, and k has what it has as the body of the function, f of y. So k is a function of y that returns f of y. But f is defined within that same environment, and f calls k. In other words, f calls k and k calls f. This is called doubly recursive. If you have a function that calls itself, it's called recursive. In this case, I have two functions. Each calls the other. Okay, now this is tricky. So k simply calls f of y, whereas f, it says if x. Now remember, x, if it's a number, if it's 0, it's false. If it's anything but 0, it's true. So if it's 0, it's going to be false. And if it's false, it will be the else equals is 1. So in other words, the function f returns 1 if x is 0. Otherwise, it calls x times the function k, and the argument is x minus 1. Okay? So does anyone want to guess what this is doing? Well, let's first of all, there's one other thing. GG is local, and it actually returns a function, the second argument, the f. It returns the f, which is the if else and if x and so forth. So if I list the environment of GG, GG is an environment. It's a local environment that has two bindings, k and f. Both are functions. So GG is a local environment that contains two functions, and those two functions will be evaluated within that environment. And what happens if I now say for I equals, this is now an example of for, I equals in 1 to 5, print, you have to print this actually to see the values, GG of I. So what happens when I call it the first time? I'm going to call it 5 times. So I equals 1, 2, 3, 4, and 5. So what's GG of 1? So GG of 1, okay, you're really calling the function, you're really calling this right here. So the argument goes in here, 1 goes in here, and it says if 1. Okay, that's true because it's not 0. So then it says x times k of x minus 1. So it calls 1 times, and then it calls the function k with a value of 0. Okay, now, so it calls k, which then it calls back to f with a value of 0, and now the if is 0, so it returns an else of 0, of 1, I'm sorry. So it actually returns 1. and you're actually finished. Now, if you, the next iteration, when it's 2, so you return, you call it with 2. So you would call this function, you would call f with 2. Okay, if 2, that's true. So it now says 2 times k of 1. So it calls k with an argument of 1, and then that calls this back with an argument of 1, which then says 1 times 0. So it calls it back. And what this is doing, it's building a stack, and it recurses back up through. And ultimately, you get a value of 2. You can write down all these steps. The logic is a little complex, I will admit. But you can actually sort of, for small values like 2 and 3, you can actually step through and see the sequence of evaluations. They keep calling each other until they get to the point where it returns the actual value. So what about 3? Okay, 3 is actually, does anyone see a pattern here? It's a factorial. This is in factorial. This is not the way you would do it, but this is actually in factorial. This is actually computing in factorial. So what is 3 factorial? 3 times 2 times 1 is 6. What is 4 factorial? 4 times 3 times 2 times 1 is 24. What is 5 factorial? 120. This is actually just computing in factorial. A very, very obscure way, nonetheless. But this illustrates the complexity with this actually kind of reminds me of my PhD thesis, because I actually had double recursion in it as part of my. I actually figured out another way to prove it. It was simpler after I had this 50-page proof, but it turned out that it turned out that I was actually doing double recursion. So this is not so obscure. But it is, you can follow through, you can follow through the logic of this, but it's actually just doing n factorial. Okay. So at any rate, you can kind of read this about the bindings. What time is it? Okay. Namespaces. You might want to play with that, with these 2 functions, and try to figure out exactly what's going on. Although I'm going to show you another recursive example that's a lot easier because it's single recursion. Remember that when I asked you in class to think about the binomial and how you could do it recursively? I'm going to show you the Poisson. I don't know if we'll get to it today. Okay, namespaces. Now we're getting back to the problem that we have a symbol, and we go through the search path, and we want to make sure we find the right symbol. So a namespace, if I write a package, I can create a namespace. And what it does, every symbol in that package that's in that namespace is exported by my package. And other people can import it. And they will know, if they tie it to my package, that they're getting the right thing. And they'll bypass the normal search path. So namespaces allow users to import symbols and their bindings from another package, as well as export if you're writing your own package. Okay. So when a package with a namespace imports bindings, it's not really put in the search path. It's put in a namespace path, but not a search path. And this can reduce clutter. So in other words, if I use a symbol in another package, I don't necessarily have to use the library function to mount the package and put it in my search path. I can just directly use it. So if I had to use 10 different packages, I don't necessarily want to have to attach each package by using the library function, which puts it in the search path. I may not want that. It causes a lot of clutter, and it may have unexpected consequences in terms of not finding the right symbols. So namespaces changes the evaluation process, because what happens is that it first of all looks in terms of your internal definitions, then it looks in terms of the imported symbols from the namespace, then it looks in the base package, and then finally it goes to the search path. Ordinarily, it would go straight to the source. I should have actually number 4 as the search path, because ordinarily it goes straight to the search path. So, if you say loaded namespaces, it tells you the namespaces. So on this particular, this is my local machine now. This is what's in these are my namespaces. Now on the other hand, there's a package called mass. And suppose I'm looking for a function LDA within the package mass. Now LDA stands for linear discriminant analysis. It's a technique we use to discriminate among groups multivariately. So it's a pretty common technique, but it's in the package mass. So if I say mass double colon, okay, then that's a function LDA, and that particular. If I just say LDA, maybe someone else has an LDA function. Maybe I've written an LDA function. This says I want the specific LDA. It's in the package called mass. So I use the double colons to do that. Now if I say if I now say the loaded namespace, notice that mass is in the loaded namespace. But is it in the search path? It's not in the search path. So it's not in the search space, but it's here. So in other words, I didn't really have to say library mass. I can still access these functions without actually using the library function, which is the other way to do it, of course. But when I if I use the library function and put all these packages on, I'm always in danger of not finding the right function. There might be several packages. You know, there are thousands of packages out there, and there are a bunch of them that will do linear discriminant analysis. And there may be multiple ones that use the name LDA. So which one does it use? Well, it just happens to be, if you don't use namespaces, it just happens to be the one you find first, which may not be the one you want. So namespaces, when you write a package, is something you should do. So if you write a package, you should use namespaces. In your own package, you know, again, you still have to be careful if you're writing a package. And we are in this class going to write a simple package. You'll be an author, except that you'll all be doing the same one, probably. Okay. How much time do I have? Okay. I want to talk about lexical scoping. We've been talking about bindings, and I've sort of danced around the idea. If you have a function, where does it find the binding of what's called a free variable? So I want to try to concretely show you what I mean by a bound variable and what I mean by a free variable. And then the question is how does it evaluate a free variable? So if I define y to be 20, it gets to be defined to be 20 in the global space, right? I just said y equals 20, so it's in the global space. Okay. Now I have a function, foo, not the same as the one before. And this says y equals 10, and then I have a function defined within the function called x plus y. So I'm going to do this. Now, what is the return value of that function? You see, I have a function within a function. And the return value of the function foo is the function, you know, x plus y. Okay. So suppose I now define, I take bar, and I say bar is equal to foo. So foo is defined down here now. And now let's let's type in bar. Well, I don't need to type it in. I have it over here. Let's execute bar. Bar returns the function x plus y, which was the last statement. That was the last statement in the function foo. So it returns that. Now, the question is this. What do you think is going to happen if I say bar of 3? Is it 13 or is it 23? That's the question. Okay, let's look at this a minute. We have y defined in 2 places. It's defined globally and it's defined within the function. Now, x, I have a function x, which is defined in the function f, which I didn't name, the function that's a function of x, which is x plus y. Okay, x is an argument which is bound to that function, but y is a free variable. Y is not defined in the function x plus y. It's defined within the enclosing function foo as 10, but it's also defined outside of the function foo as 20. Okay? So where did it find it? Okay, well this gets into the concept of this gets into the concept of the scoping rule of the particular function. So first of all, a function has a function as its return value. And we then bind that to foo in the global environment. So I've discussed that. And then functions such as foo that have an enclosing environment are called a closure. So this is a function closure in particular. And we can do that in several ways. We can create a function closure explicitly, as we did here, or we can actually attach an environment to a function, which we did before, and I'm going to do again. So there are a couple ways that we can create a closure. I defined a function enclosure I defined a function closure explicitly by the creation of a function in an environment here, but I'm going to define it differently before. The point is that it found the value y within the function closure. It did not go out to the global environment. A dynamic language would go out to the function, at least potentially would go out to the global environment if you had a dynamic language that had a different scoping rule. In this case, it used the local value of y defined within the function foo, which was the same place that the function was defined. Okay. I thought I explained that a little bit more. I probably need to give a little more text on this. Let me do one more thing before we quit. And that is where I'm going to define bar 2, which is a function x plus z. And then I'm going to define a new environment, E1. And I'm going to bind a variable z within that environment, E1. And then this gets into this try-catch, which was in the first section. The question is, what is, if I say bar 2 of 11, what do I get? Okay, bar 2 failed. It didn't work. Now, suppose I assign bar 2 to the environment E2. So I use the environment function and I say bar 2 is now defined in the environment, excuse me, E1. If I do that, and now I execute it, I get the value 31. Okay, so 1 plus 20 is 31. Yeah, so this is the second way you can define an environment for a particular function. Well, so you might ask, why is this relevant? Why is this relevant? I don't have time to do this today. In calculus, you will learn something called function optimization. Or you might say, okay, here's a function. How do I find the maximum of that function? Or I want to find the value of x such as f of x equals 0. Well, let's just take the maximum. I have a function. I want to find its maximum. So how do I do that? How do I find the maximum function? Can anyone tell me?
The slope is 0.
Yeah, it's the value where the slope is 0. So what's happening, what's happening is I'm going to take the derivative actually and set it equal to 0 and solve that. In statistics, we call that a score function. So if you're in a simple calculus course and you're trying to do function optimization, you actually do that in a very simple way. If you know derivatives, you take derivatives set equal to 0 and you solve for it. And a lot of times we use something called Newton's method in order to do this. It's an iterative way that we can approximate the value of x that gives you f of x equals 0 for the derivative. The problem is with statistics, it's not quite that simple, because we actually want to find a parameter estimate. The parameter estimate depends on the data. So we have a parameter estimate like mu or something, and we want to find the value of mu that is the maximum given the data. So in other words, we have to do an optimization based on data. So that we have a more complex situation, and we have a technique called maximum likelihood estimation. And maximum likelihood estimate says, well, what is the maximum value of mu given the data? And that's based on something called the likelihood function, which depends on the parameter mu as well as the data. So when we write an optimization function, it's a little bit harder. But it turns out with lexical scoping, it becomes fairly easy to do this. And if you didn't have lexical scoping, it would not be easy. By the way, S+, which both R and S+ derive from S, they do not have the same scoping rules. So S+ uses dynamic scoping, whereas R uses lexical scoping. So if you write a program in R, it may not run in S+, or vice versa. And S+ is a commercial version of S, which is the underlying language. So at any rate, you should finish the rest of this chapter. This is taking a little longer to get through than I thought. But basically, what I want to show you is how do we use lexical scoping to get maximum likelihood estimates? And you're going to see why lexical scoping becomes pretty important. This is not just some abstract notion that we need. It turns out that it makes estimation. To write a likelihood function and find the maximum of it turns out to be trivial in R. Not trivial, but easy. Whereas if you didn't have lexical scoping, it would be much harder. So we don't have too much more to do. I've got to figure out what's going on with the